Internal flows can either be laminar or turbulent. For an internal flow, we typically think about the transition from laminar to turbulent as a Reynolds number of about 2300. So RE based upon the diameter less than or equal to about 2300 is considered a laminar flow, where molecular diffusion controls the mixing processes, and obviously greater than 2300, we consider this to be turbulent. And in the turbulent flow, it's the flow itself that causes the mixing. So it's the eddying and the in-depth velocity fluctuations that causes mixing. If we were to look in a laminar flow and look at the velocity profiles we're looking here at the bottom, a laminar pipe flow has a parabolic velocity profile, whereas the turbulent pipe flow has a much flatter velocity profile but sharp changes in the near wall region. And again, it's the intense mixing that's occurring here that's causing this flat profile. It's often important for us to understand what the mass flow rate is in internal flows. And the mass flow rate with units of kilogram per second is really equal to, in a very simple sense, the density times some bulk or average velocity times the cross-sectional area. Notice that UBAC is really a volumetric flow rate, so it's a volumetric flow rate with units of meter cubed per second times the density with units of kilogram per meter cubed that gives us this kilogram per second. In an integral sense, because U is in fact a function of R, we know that this is rho U of R dAc, where dAc is the differential cross-sectional area. And we know that dAc can be written as 2 pi r dr. In terms of the average or bulk temperature, it's a little bit more complicated. So the bulk temperature, notice, is defined in terms of a velocity also. And the reason for this is that we want the bulk temperature to be energy conserving. So that's the thing that we care most about in problems of this type. So over here we have m dot Cp Tb, which is in some sense a enthalpy mass flux, or enthalpy flow rate. So that enthalpy flow rate in an integrated sense is equal to rho u Cp T 2 pi r dr. And that's the definition that we use to understand and to evaluate that. So Tb is rho u T of r, so both u, and I'm going to write this a little bit differently so it's clear that both u is a function of r, t is a function of r. We have our differential cross-sectional area divided by m dot. So we've divided Cp out of the system. I need you to understand that the bulk temperature has the velocity profile in it. It's not simply an area average. So a common mistake students make is to think that the bulk temperature is just equal to the temperature distribution integrated over the area and divided by the area. This is not true. This is not the case. A simple case to make this clear is, imagine that you have a flow in a channel, say, as compared to a tube, because it's just a little easier to understand, and you have half of the channel has a fast flow, and half of it has a slower flow. So here's the velocity in the channel. at the same time, you say that the fast flow has a temperature, for example, of 100 degrees C, and the slow flow has a temperature of 20 degrees C. So from the perspective of this system, we wouldn't think that the average or bulk temperature would be 60 degrees C, which would be some simple average of these. It would be closer to 100 degrees C because we have to weight this by the velocities. So you want to think about this T bulk really as the velocity weighted. So V1 T1 plus V2 T2 over, and in this case it looks like the average velocity in the system, because the average velocity is a different issue from the average temperature. So as V2 gets large compared to V1, the temperature looks much more like T2. So we're often at times going to work with the bulk flow energy balance. And so in terms of the bulk flow energy balance, we have an enthalpy flow in, an enthalpy flow out, and we have a Newton's law of cooling term on the perimeter or the periphery of the control volume. So we have some control volume. We're following or interested in what's going on there. This control volume has some length delta x. Energy in is equal to energy out. So the way we formulated this, energy in is this Newton's law of cooling plus the flow in at the left side. Energy out is the flow out at the right side. We simply use the definition of a derivative or a Taylor expansion, whichever one you feel comfortable calling it. And we're looking at terms that look like m dot c cp tc x plus delta x minus tc x. When we divide through by delta x, this first term becomes, in the limiting process of delta x going to 0, dtc dx. The second term is not dependent on delta x, and we simply get the Newton's law of cooling term. So one of the things that you might ask is what happened to the conduction or the diffusion term. We'll show later on that these problems are formulated in something called high Peclet number limit. The Peclet number is analogous to the Reynolds number. It's an average velocity or mean velocity for a pipe flow times the diameter divided by the thermal diffusivity. And when this Peclet number is large compared to 1, we can neglect the effects of diffusion. So this alpha represents diffusion or conduction processes. So we can neglect diffusion relative to the flow. The top, the numerator, is a flow effect. And so this is a powerful model for understanding internal flows, and we're going to spend most of our time really looking at problems of that type.